Well, it was a practice day today, and so here's what I'm hoping. I'm hoping that you have already taken a look at the questions in the worksheet for today, and by worksheet, I just mean digital document with old questions that I've used on exams in years past. I have drawn on my experience as an AP teacher to provide a bunch of questions, and hopefully you have taken a look at these, and hopefully you've even taken a look at my answers to these, because what I'd like to do is point you in the right direction on some of them, but not all of them. So I'm going to spend about 10 minutes or so giving you some good pushes in a good direction, but then the rest is up to you and up to me when we gather in office hours. So this area is all above the x-axis. And so that area is a definite integral. If that area was some above the axis and some below the axis, we'd have to break things up, but we don't, because we can just take the integral from 1 to 2 of 4x cubed plus 2 dx and know that this is going to give us the area we're looking for. We find an antiderivative, sub, and subtract. Why? Because this is a number and this is a number, and we're looking for an integral value, not a derivative value. And so fundamental theorem part 2 says number, find an antiderivative, subtract. Antiderivative of 4x cubed, antiderivative of 2. You can confirm that the derivative of this is that. Now we sub, and subtract, and we've got it. Again, this is one of the easiest questions I could give. That's why it was question 1 back in the day. It is a very straightforward question. You have got to know how to do this. If you don't know how to do this, everything else is trouble. Similarly here, this is not terribly difficult, so I won't spend too very long on it. I will remind us that this is x to the negative 2, and so the antiderivative of that is negative x to the negative 1. We sub, and subtract. I'm pretty sure the answer is C. That seems reasonable. Negative 1/2 minus negative 1. Yes. Okay. So this is similar to something we have actually done in a previous video, so I'm not going to belabor the point. You've got cosine x, you've got 0 to k. I think this might have been the inspiration for the question I wrote about that. So sorry. It's not from 0 to k. It's from k to pi over 2. So the integral from k to pi over 2 of cosine x dx is 0.1. So I'm going to ask you to remember antiderivative, substitute, subtract. You can do that, or failing that, because this is a calculator active question, you can tell all the choices have decimal answers. You can just try those different values for k and see which one gives you the area of 0.1. Love this question. Love this question, because it makes us recognize that this lingo, the derivative of capital F, is little f. So that means that capital F is an antiderivative of little f. And that means that when we see this means that capital F of 3 minus capital F of 1 is 2.3. That's what that means. Because how do we do definite integrals? We take an antiderivative, sub, and subtract. So this question is interesting because this question says go the other way. When we see a definite integral, we can write it in these terms. When we see this sort of a setup, we can write it in these terms. What is that? Well, the question says that this part has an area of 2.3. And this part, because I passed elementary school, has an area of 2. And so together, there it is. There it is. Again, I can go through a little bit faster than I would in class. I would never go this fast in class, but in class you can't hit a pause button and go back and rewatch. So I suppose that is a good thing. This is a reminder about the Fundamental Theorem Part 1. The Fundamental Theorem Part 1 says if we're looking for a derivative, this is a derivative of an integral function where that's an x. The derivative of an integral from that's a number to x is this with that subbed in. So capital F prime of x is the square root of x cubed plus 1. So capital F prime of 2 is the square root of 2 cubed plus 1. 8 plus 1 is 9. Take a square root. Same sort of thing happens here, looking for where G has a maximum. We know that G has a maximum where G prime changes from plus to minus. What's G prime? Well, G prime is the derivative of an integral. That's a number. That's x. So we take this with that subbed in. So now we put these two pieces of information together. We want G prime to change from positive to negative, which means we want F to change from positive to negative, and F changes from positive to negative at C. Same kind of thing happening here. Where is F a minimum? F is a minimum where F prime changes from negative to positive. Well, what's F prime? F prime is the derivative of an integral function. That's a number. That's a function of x. So F prime is this with that subbed in, right? But then chain rule says that because this is not x, it's a function of x, we multiply by the derivative of that inside piece. So how does this look? Well, this part is always positive because it's e to the something. So this is the only part we care about. It changes sign at 3/2. It's negative on one side and positive on the other. You can check, set that equal to 0, plug in your favorite number less than 3/2 and your favorite number bigger than 3/2. And you can figure that out. It's not terribly difficult. F prime changes from negative to positive at 3/2. Same sort of thing's going to happen over here. Looking for where G is decreasing. G is decreasing where G prime is negative. G prime is negative. Well, what's G prime? G prime is the derivative of an integral function. That's a number. That's x. So we use this with that plugged in. And your calculator does the rest of the work there. You graph this function and look for where it is below the x-axis. One other thing I wanted to give a good hint on was this question. So we're looking for an approximate value of velocity, and we have this acceleration function. So we haven't done enough work with tables, so I'd like to do a little bit of work with tabular data. 5, 2, 8, 3. You're looking to do a left-hand Riemann sum. So this is an acceleration graph. If we find the area under an acceleration graph, it should give us a change in velocity. The integral from 0 to 6 of the acceleration is approximately, well, that's 5 times 2, that's 2 times 2, that's 8 times 2, that's 16, and 4 is 20, and 10 more is 30. This is the change in velocity. Notice it's an answer choice, but this is the change in velocity. So the velocity at time equals 0 is 11 feet per second. So if it was 11 feet per second and it changed by 30, that's where it ends up. So of some importance to you is the recognition that an integral is a change in a quantity, which usually matters. And it's a way, and we can approximate those integrals using left-hand Riemann sums, which is something we haven't done in about a week or so. Okay, I went to 12 minutes instead of 10, so sorry. Hope these 12 minutes are helpful.